All right, hey everyone. So this is chapter 5, chemical reactions. Um, I've posted some more stuff in Cougar View. So if you go to Cougar View content, chapter 5, a bunch more links here. So once again, these are not required. These are uh, practice problems, examples, introductions to certain topics from different teachers. So if you find anybody that you really like the way they teach or their style or makes more sense to you than the text or the PowerPoints or whatever, then you can dive a little deeper, and most of them have videos associated with every topic that you'll see here. So don't be scared to go find other resources to try to get as much knowledge as you can. And the more practice you do, the more times you see it, the easier it'll get. Okay? So this is kind of a long chapter. We're going to go ahead and jump right in. Today we're talking about chemical reactions. So we've talked about chemical and physical changes, right? Like physical changes had to do with changes in state, like going from ice to water or water to vapor. Okay, these are not changing the actual chemical formula. It's always going to be H2O. It's just become frozen H2O, or it is now it's water, right? Liquid H2O, and then it could even boil off and become gaseous H2O. So these are all physical changes, and as such, doesn't change that chemical formula of the compound. Now, a chemical change is when that formula does change. Okay, so we've talked about the different signs of a chemical change. Produces a smell. It heats up, gets real warm or hot even. Uh, Produces bubbles. Right. We saw carbon dioxide bubbles in one of the labs, I believe, or we will see. Excuse me. In one of the labs, you'll see carbon dioxide bubbles form. Okay, from certain reactions. So, with that being said, a chemical reaction is just when a chemical change occurs, which changes the chemical formula of the molecule. Okay, remember we don't change. You can't change atoms outside of you know radioactive atoms. Atoms do not change into other atoms. So any changes in a chemical formula would has to preserve the same number of atoms. Okay? But if I change that formula anyway, that would be a chemical change, and most likely I would see evidence of that chemical change, color change, bubbles, some kind of heat produced or smell, whatever. All right. So we have these different terms when we're talking about that. We've been writing chemical formulas, but now we're going to start writing chemical equations. Okay, so chemical equations are just uh, the representation of that chemical reaction in a way that makes sense for us. Okay, so we've all kind of came up with these standardized ways of writing chemical equations, and a lot of times they'll look something like this. Let me get one that's a little simpler. Okay, oh, go back. So N2 plus 3H2, actually I like this one here. CH4 plus 2O2 because it shows me the atoms here. Alright, so notice that I still have the same number of atoms on the left that I do on the right, but they've changed position, they've changed arrangement. The bonds have been broken and then put back together. Okay, so this is the chemical equation. It's usually written out like this on the bottom, but more likely you'll see it like this right here. And we'll talk about these parentheses here in just a minute, but these are important as well. These indicate the physical state of these molecules. All right, so everything on the left is the reactants, everything on the right is the products. All right, and you'll read it just like a sentence. Two hydrogen combines with O2 to produce two water molecules. Okay? And I'll break down each individual portion of this, but I just want to kind of introduce. Look, they use the exact same one. The reactants are on the left, products on the right. The coefficients were those numbers in front of the molecule that I mentioned. Okay, so the 2 in front of O2 is a coefficient. This little 2 behind it is a subscript. All right, so it's important for us to kind of keep that straight, what the difference between the subscript and the coefficient is. Let me pull up my paint program real quick. And kind of show you what I'm talking about. So the subscript goes behind, let me make that bigger. Alright, I'm going to write my O right here, the O2. Okay, so if I have this subscript behind the chemical symbol, that means there's 2 oxygens, just the oxygens. Now when I put a coefficient in front of it, that means I have 2 of everything behind it. So there's 2 oxygen molecules. All right. Let me do another example with that CH4. So let me clear that. CH4. Okay, so now the 4 is a subscript, indicates that there are 4 hydrogens. Okay, just 4 hydrogens. There's not 4 carbons. So if I wanted to indicate that there are 4 carbons, but no change in the hydrogen, I put the 4 behind the carbon. So now I have 4 carbons, 4 hydrogens. All right. And one more little thing. 4 in front, the coefficient. Remember, if it's in front of everything, it's the coefficient. This means there are 4 of everything right behind it. So 4 methane. CH4 is a methane. That means I have 4 carbons here, and I have 16 hydrogens, because each methane has 4 hydrogens. So if I have 4 methanes, that makes a total of 16 hydrogens. Okay? So I hope we get that straight on the coefficient. This is important for when you go to balance chemical equations. You're going to need to make sure you keep straight what the subscript means and what the coefficient means, because you have to have the same number of atoms on both sides of the equation. Okay? So let me go back to our PowerPoint. I'm actually going to go to the text as well, because I want to make sure I keep up with where we are in the text. Alright. Good there. Chemical reactions. Writing chemical equations. Okay? And the reason there are the same number of atoms on both sides is because of the law of conservation of mass. Okay, so it says that matter cannot be created or destroyed. So if you're in a closed, we call it a closed system, where things can't get out or get in, then you, after a chemical reaction, you will always have the same number of atoms as before the chemical reaction. Okay, you've changed them around, you've broken bonds, you've reordered them, but there will always be the same number of atoms on the left side as there are on the right side. And part of balancing chemical equations is you making sure that there are the same number of atoms on the left and on the right. All right, so when we start balancing chemical equations, that's going to be a big part of it, is making sure you have the law of conservation of mass, right? You have the same number of atoms on the left as you do atoms on the right. All right. Oh yeah, the symbols. So remember we talked about physical states, physical changes being between liquid, solid, gas, whatever. We like to indicate those in chemical equations. So usually, like here, we'll see the CH4 with a G behind it. That means it is a gas. All right. The O2 with the G behind it is a gas. Let me find something that's not a gas. Uh, this is a good example here. Okay, so this is, the S is for solid. This carbon dioxide and water has been combined to make something solid. The water is liquid. It's usually indicated with an L. And then the only other one you'll see is aqueous. I don't see an example here. Um, so here you see the S for solid, L for liquid, G for gas, and then the other one is aqueous, and that just means it's an ion, right? It has some kind of charge or it's dissolved in water. It doesn't necessarily have to be an ion even. If it dissolves in water, it becomes aqueous, and that's what we say with the AQ. And a lot of these reactions are going to be aqueous because that's how we introduce things, right? We mix it up. If we can mix it up in a liquid and then add it to something else and then create the solid from that. So you'll see what I mean as we do more reactions. As you get into the lab, you'll see some of that. So this corresponds with Lab 5, chemical reactions in Chem 21. So make sure you're watching this before you go and do that. All right, so here's some practice problems. Label reactants and products. Label how many, indicate how many atoms of each type of element are present. And remember, you have to have the same number of atoms on both sides. All right, so now let's get to balancing chemical equations. Uh, so everything that you've learned up till now, I don't know why this looks so bad. I might need to load this on something else. Everything that you've done so far, whether it be the charges, right, determining of valence electrons and charges, um, being able to pair up different anions with cations, that's kind of setting you up for this balancing of equations. Okay, so when you start doing ionic equations, you're going to have to balance charges and atoms. So it gets a little trickier even. But first, let's start with just balancing regular equations. So number one rule is to make sure you have the same number of atoms on both sides. All right, so this is going to walk through step by step. Um, Here is the problem. I don't guess y'all can see this as well. If you open it up in PowerPoint, it should be straight. But write a balanced equation for the reaction of propane C3H8 with oxygen O2 to form carbon dioxide and water. All right. So the first step is just to write that equation down. They might give you this chemical formula. You might need to know what it is. If it says carbon dioxide, for example, you should know that that's CO2. All right, based on your naming, how you learned to name things. So first thing you'll do is write out the equation. Now I need to start getting ready to balance. Let's start with the C's. All right, always start with your carbons because they are most central to most reactions. I won't say all reactions, but they're the easiest to deal with. O's can get kind of tricky, so we usually save them for the end. So balance the threes. I have 3 carbons on this left, so I'm going to add a 3 to this right. Now I have 3 carbons here, but this is a coefficient, and I can't add it as a subscript because that would change the molecule. It'd no longer be carbon dioxide. It'd be, tricarbon dioxide or something. Add the 3 in front, but then that means I have to go through and balance something else because that changes the number of oxygens I have now. See, the oxygens were not balanced, but now I have 6, 7 oxygens on the right. That's going to be hard to balance with an O2 because I can't get 7 oxygens at O2, right? I can't split up oxygen to make 7 atoms if they're all coming in O2s. So next we're looking at the H's. You'll go from the C to the H and then balance on both sides. So start on the left, I count my atoms. I have 8 hydrogens. There's 2 tied up in water, so if I multiply that times 4, that gives me my 8 hydrogens. Alright, so now I have carbons and hydrogens balanced. I'm going to move on to oxygen. Oxygen has 4 on the right from the water, and then 6 on the left from the carbon dioxide. That makes 10. So if I multiply this O2 by 5, coefficient of 5, that'll give me 10 total oxygens. Okay? So it's really just simple addition and multiplication. You're just trying to make sure that the atoms are the same number of atoms are on both sides, and you haven't changed a chemical formula to make a new molecule. Okay, those formulas, C3H8, O2, CO2, H2O, they have to stay the same. Okay, all of your balancing needs to be in the coefficients. All right. So that should get us through balancing chemical equations. And like I said, I put a bunch of videos. There are practice problems for specifically balancing chemical equations and working more difficult chemical equations. Like when I was just saying that I had 7 oxygens, I needed to have 7 oxygens, but I can't break down an O2. Those end up being fractions. So you will see some balancing of chemical equations that have fractions, and so I wanted to put a video in there, an example problem where you get to see that one time. Alright, so check out your content. I have a practice problem in there that goes a little more in depth with the balancing of chemical equations. We've got a lot to cover today, so I'm not going to go through and work any more examples. But your text, as you see here, has a bunch of different problems that you can kind of practice on and keep working. One thing I do want to mention right here is polyatomic ions. Polyatomic ions are put in the parentheses. So let me see if I can zoom in right here. I don't guess I can. But this top problem, let me see if I can get it in the middle. I know how to do it. Alright, so right here I'm looking at calcium phosphate plus sulfuric acid. So there are a couple of polyatomic ions here. One is the phosphate, right? Now the only reason you would put this in parentheses is if you need to make multiple phosphates. You see the little 2 subscript behind it? That lets me know that it's just the phosphate that there's 2 of. But it is all of the phosphate. So there are 2 phosphorus, there are 8 oxygen in this first part of the chemical equation. There are 8 oxygen in that calcium phosphate molecule. Alright, 3 calciums, 2 phosphoruses, and 8 oxygens in that one molecule. And that's, I get all that information from these little numbers here, the subscripts and subscripts, and then the polyatomic ion subscript behind the parentheses. So the parentheses lets you know that it's all one polyatomic ion essentially, and that needs to stay together. When you move that to the other side, it needs to stay as PO4 when it moves to the other side. Now you might not have to put the parentheses because the parentheses is just letting you know that there's multiple phosphates. Right? Sulfate, for example, is on the right side, but there's only one of them, so I don't need to put the parentheses. But when I read it, I do need to recognize that that's a polyatomic ion, that's sulfate, okay? And this one on the left is phosphate. So calcium phosphate and sulfuric acid is a little bit tougher of a balancing equation. So this will be a good practice problem. If you can get in there and do this, the book obviously helps you walk through it, but give it a shot on your own and try to get through it and balance this problem, and you'll be well on your way to solving any of the other problems you'll see in this course. Okay? Alright, go back to PowerPoint. Alright, so we're all the way down to types of reactions, and as I said, I'm trying to keep up with both sides. So there are several different types of reactions, and most of them can be kind of illustrated with these little A-B combinations. So A plus B to form AB together, right? That is called a combination reaction because I'm combining two things and I'm making one. All right. There is a decomposition reaction, which is the opposite. I'm taking one thing and I'm breaking it apart, making two individual components. So that would be decomposition. AB yields. This little arrow pointing across, so you have reactants on the left side. Yields is that little arrow. We like to say yields products on the right side. So AB yields A plus B. That would be a decomposition reaction. All right. What else do we have? Single replacement and double replacement. So this is basically me just switching out one of the components for another one and creating a new molecule uh, with one of those components in a single replacement. In a double replacement, I'll replace both of them. So here's the AB diagram. A plus BC yields B plus AC. You see the A was the solo component on the left side, on the reactant side, and B is the solo component on the right side. Um, C is always combined with something. It was a single replacement. I've only changed out one molecule. If I look at double replacement, AB plus CD equals AD plus CB, that is a double replacement. Both components have swapped sides. It's essentially a double flip. Okay, so we call that a double replacement. Um, these are actually these are going to be easier to recognize, so you ought to be able to run through here pretty fast, but do these practice problems. Make sure that you understand. I have got to unzoom this thing. I forgot I zoomed it in for that equation. Just a second. All right, let me scroll back up here because y'all actually probably could still see the diagrams because I went right by them. Just to make sure we're on the same page. Combination, yeah. A plus B, decomposition, AB splits to make A plus B. Single replacement, I'm just moving one. So C is combined with B in the first, and then it's combined with A in the second. Double replacement, I flip them both. And we also have redox reactions, which we call oxidation and reduction. And that is where you change the electronics of that atom or the molecule. Okay, so redox reactions are essentially moving. We've looked at valence electrons, so you had this idea of a charge being on a molecule. Now, if I take, for example, a copper ion, and I think you can still see this, a copper ion, right, that is positively charged, it's given up 2 electrons, it's got a 2 plus there on the copper, and then it goes through a reaction and picks up 2 electrons, right? So what I've done is I've changed the charge of the copper, and as such, I've changed a lot of the properties of the copper, um, and allow it to make different reactions, right? If I had the 2 extra electrons there, I might could use them to do something else. So all of this changes the properties of that copper. And changing that is essentially a chemical change, and we call that a redox reaction or oxidation reduction. Redox is like a shorthand term. Let me see if they use it anywhere here. Yeah, redox reaction. Okay, oxidation reduction. So, oxidation just means that it has lost electrons. Reduction means that it's gained electrons. And that's just something you're going to have to kind of keep up with. I think they said uh, there's like a what we call a mnemonic tool. It's called Oil Rig. Yeah, Oil Rig. Let me write that down for y'all. So clear, new, don't save, and it's probably going to be in the text or the PowerPoint here in just a second, but I'll go ahead and write it. Oil rig. So oxidation is loss. I'm going to write kind of sloppy because I want to get through it. Oxidation is loss of electrons. And then rig, reduction is gain. Okay, so reduction is gain of electrons. Okay, so I'm going to put a little E minus, that means electron. Oil rig, that's kind of how you can keep this straight. And so when I look at a problem, I'm trying to figure out which is the atom being reduced, which is the one being oxidized. I'll look for the change in that charge. So here the copper gains 2 electrons, so it'll be the one that's reduced. The zinc loses it, so it'll be the one that's oxidized. And then vice versa, we call them agents. So the zinc, if it's the one that's oxidized, is the reducing agent. It causes the copper to gain electrons. And the copper is an oxidizing agent because it is reduced, causing the zinc to lose electrons. Okay, so you see it can get confusing. That's why I like to use this oil rig kind of terminology to keep it straight. Y'all remember that, and you should be able to answer any questions about this. Now, balancing these are a little difficult too because, as I said, you have to kind of keep up with the charges as well. Um, but we'll see what all is asked of you in ALEKS and whatnot. And so I don't want to get too in depth with this because these can get kind of tricky. But redox reactions are the way we get a lot of these energy type reactions done. Batteries, for example, are a good example of redox reactions taking place, moving those electrons around to different areas, stacking them all up on the negative end so it can flow through the circuit and recycle back into the battery and create a current, right? So, very important in chemistry, but I don't want to get stuck in the weeds there because we got so much to cover. And you'll see in the body, we use a lot of these too to nerve impulses. Um, the heartbeat is an example of building up this potential through redox reactions, and then it creates the causes the heart to beat. It's really cool stuff. But anyway, let's keep going. We got to talk about mole and Avogadro's numbers. So now we're getting into some more of the math. I'll try to do a couple examples on a calculator. Um, Acid-base reactions, I didn't mention this. Let me make sure y'all can see this. So acid-base we'll come back to in chapter 9, but that's just when you mix an acid and a base, they neutralize and create water. So we also call that a neutralization reaction. Um, if you do see that, it can be called it's acid-base, but also neutralization reaction. But we haven't discussed what an acid or a base is, so I don't expect them to really quiz you on that. I hope they wouldn't anyway. All right, and so more examples: combination reactions, decompositions, single replacement, double replacement, oxidation, reduction, redox. In other words, keep on going, keep on going. Now we're at the mole. Okay. So the mole is just a way of counting atoms. All right. We talk about atoms are so very tiny that you would stack trillions and trillions and trillions of them in the palm of your hand. Right. So uh, it's hard for us to kind of wrap our head around those kind of numbers. So what we do is we use uh, a different system to kind of calculate the number of atoms or the number of molecules that we're talking about. Okay, this system is the mole and Avogadro's number. Okay, so the mole you ought to think about like a dozen. Let me pull up my paint thing, clear this. Um, it's like saying a dozen, only it represents a much greater number than a dozen. So let me just say a dozen. Do that. 1 dozen equals 12, right? If I say I have a dozen of something, I have 12 of something, okay? So a mole of something, now this is where it gets pretty crazy, equals 6.022 times 10 to the 23, uh, whatever, anything. Okay, so a mole is equal to this many something. All right, just like I say, I have a dozen roses. If I have a mole of roses, I have 6.02 times 10 to the 23. Just in case you're not clear about like what that looks like, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So I'd have to rearrange commas, but this is the number. Oh my goodness, I didn't put it on there. Okay, I apologize. I'm going to back up just a second. So dozen equals 12. Mole equals this number here, 6.02 times 10 to the 23. And then here on the bottom, I've started writing out that number. You see how crazy big it gets. So um, we use the mole to simplify it, right? I can just say I got a mole here. Or I can say I got a half a mole. I got 0.683 moles, right? It's an easy way to represent large counts of these numbers. So I just say that the mole is the count. It's how many of these atoms that I have. Okay. Now, one way that is actually good for us, the way that the periodic table is set up and whatnot, is that this is the atomic weight that you see on the periodic table is directly proportional or is the uh, molar mass, what we call the molar mass. I mean, can't get my video to come back up. Oh, here it is. Okay. So mole, I'm back on the PowerPoint. I couldn't get my PowerPoint to come back up. So mole of carbon atoms is 6.02 times 10 to the 23. This is just saying that a mole is always the same amount. Now, one thing I want you to keep in mind is, say I have 1 mole of H2O. Let me pull this back up. 1 mole of H2O. All right, 1 mole. Make sure y'all can see it. 1 mole of H2O means that I have 2 moles of hydrogen and 1 mole of oxygen. You see how that works? Right? Like if I take a bike and I break it down, say I have 1 mole of bikes, and then I break it down into tires and frames, I'll have 2 times as many tires as I do frames. So I have 2 moles of tires and 1 mole of frames. So, as I said, mole is just a way of counting, and you'll get more comfortable with it as we go along. Okay? But just always remember that a mole is equal to this many items, things, particles, atoms, whatever. Okay? That's the text. All right, these are the conversion factors, how you would kind of set it up. How many molecules are contained in 5 moles of carbon dioxide? So I would just multiply 5 times 6.02 times 10 to the 23. Okay? And that's what they set up here. As I say, you can open this up in Microsoft Office and it shouldn't be stacked up on top of each other. It shouldn't be that way anyway. I'm going to go to the text where it's a little clearer. Yeah, so 5 times 6.02 times 10 to the 23. And that'll give you the number of molecules that you have there. So pay attention to what they're asking too. Molecules versus atoms. It might ask you to tell me how many carbon atoms are in 3 moles of carbon dioxide, or how many oxygen atoms are in 3 moles of carbon dioxide. So you have to pay attention. There's 2 oxygens in every carbon dioxide, so then it'd be 2 times 3 times 6.02 times 10 to the 23rd. And then if you want to convert the number of molecules to moles, you can just divide. So I like the way they set this up. They write out the conversion factors. You can go through here and practice. All right. So now let's talk about the weight, molar mass, molecular weight, all of these things that we use um, to determine the number of moles. Okay, so I can't sit there and count individual atoms. So what we do is we weigh however much it is, and then we can calculate how many molecules that is based on the weight of each individual atom. The weight of each individual atom, luckily for us, is on the periodic table. It's the atomic mass, right? So that is also called the molar mass. And what that means is there are, let me pull up a periodic table real quick. Periodic table. Let's start with carbon because I think your book starts with carbon. 12.011. So that means there are 12.01 AMUs. It was the atomic mass unit that we learned originally, but also grams per mole, which is the molar mass unit that you're going to use pretty much from here on out. Let me pull this up. Okay, so 12.011 grams every 1 mole. All right, so it's interesting that it all sets out this way. It's kind of the way we created it, or scientists have created it, so that 12 grams of carbon is exactly equal to 1 mole, or 6.02 times 10 to the 23rd number of carbon atoms. All right, so that many number of carbon atoms, this many number of carbon atoms is equal 12.011 grams. Okay? And so you'll use this conversion factor of 12.01 grams per mole, or whatever molar mass that you're using, to try and calculate the number of moles or the weight, or you might use the weight and the moles to determine a molar mass. But just like the density, you'll get familiar with these conversions and going back and forth between the two. But everything you need there is on the periodic table. If I have, say, methane as one of my reactants, I can do carbon, which is 12.01, plus, and we'll just round off to 12, plus hydrogen, which is 1.08. So that'd be 13, but I got 14 I got 4 hydrogens, so it'd be 12 plus 4, 16. The molar mass of CH4 would be 16 grams per mole. Okay? So, Cougar View, like I said, I got a bunch of those videos. This is a good portion for you to kind of go in there. Some of them have better illustrations and explain this more thoroughly, but I don't want to use up the whole lecture day on that. So go in there, check out what they got. I'm going to hit on a couple more little points. So we said that mass is also AMU, that the molar mass is also the atomic weight that we were first introduced to. So AMUs can be also expressed as grams per mole, and that's all this is saying. And the molar mass of water is 18.02. You can write that both ways depending on which way you need to calculate it. I might do an example problem here. Yeah, let's do this example problem. Identify the original quantity and the desired quantity. How many moles are present in 100 gram of aspirin, and they give us the molar mass. Okay, so I'm going to pull up my paint. 180.2 grams per mole. Let me write that down first. 180.2 grams per mole. And I'm going to write 1 mole just to make sure that I can still see it and clearly move my mole unit. Okay, 100 grams of aspirin. Sorry, I had to pull that up and look at that. So now this is where I decide which way I want to put my conversion factor, right? So if I want to multiply this times 100, but I want to leave mole on top. Mole has to be on top because that's the answer that I'm trying to get. So this needs to flip, right? To get mole back on top. So let's do that. 1 mole over 180.2. And then times 100 grams over 1, just for simplicity. And that would be grams canceled. I got a gram on it there, so those grams cancel. 100 divided by 180.2. I'm sure that the PowerPoint will do it, so let's look. 100 divided by 180.2 is 0.55 moles. Okay? And that's the answer that I was trying to get on the right side was moles. So that's a very simplistic problem for molar mass, determining the moles of a substance using the mass that you have available. Alright? And so you can always calculate the molar mass. Let me go back here. I want to illustrate one other point. They gave us the molar mass of 180.2, but I could calculate it if I go through and multiply, 9 times the molar mass of carbon, which was 12. Sorry, let me pull this back up. 9 times the molar mass of carbon, which is 12, so it'd be 9 times 12, it'd be 92, 82, 98, 108 plus the hydrogens, 8, 116 plus 4 times molar mass of oxygen, 32, will be 180.2. Okay? Oxygen is 16. So you can calculate the molar mass of any molecule just by going to the periodic table, getting the atomic mass, and then calculating it up. So let me clear this off. Molar mass, there was 9 carbons, so 9 times carbon, which is 12 grams per mole, right? And that'd be 108. 8 times hydrogen, which was 1 gram per mole. And 4 times, I think 16 is oxygen. Grams per mole. 64. 72. 72 plus 108 is 180. Alright? So that's how you can calculate the molar mass on your own in case they don't give it to you. Alright, just in case you see that later. Alright, now what else? So they do a lot of practice problems here. These are obviously really good to go in and try and work on your own. Alright, And now this last portion, we're actually going to combine the two things that we've learned in this class. Okay, so we learned how to balance chemical equations, right? And we can say that if I give you a chemical equation, you can go through and balance the coefficients to make the atoms line up on both sides. Now what you'll have to do is use those mole ratios, or what we call them, uh, to calculate the mass that was acquired in a reaction, or the yield is what we like to call it, how much product was yielded. Remember, we got reactants on the left, products on the right. We're looking at how many products we can make. Let me go back to the bike scenario. Let me clear this off. So, say I am the owner of a bike factory, right? And I've got to make a bunch of bikes. Now, a tire plus a tire plus a frame. This will be my frame here. Alright, that will equal a bike, one bike. Alright, so another way of me writing this equation would be 2, and I'll put little spokes on here so you know that these are wheels. So 2 wheels plus a frame yields a bike, okay? This is how I like to think about chemical equations, because this is essentially what we're doing. We've got these pieces and we can put them together in a certain way to build certain things. Alright, yields one bike. Alright, so now if I gave you a problem and I said, hey, I have 21 tires, okay, and 5 frames. I got 21 of these little ugly tires that I got, and I got 5 frames. How many bikes can I make? Right? Well, I can't make 10 bikes just because I have 20 tires, because I don't have enough frames to fill the bikes up. So this is what we call a limiting reactant. I can only build 5 bikes because I only have enough materials for 5 bikes. Even though I got all this extra bike tires over here, they're still going to be just bike tires. So I can build, I'll use 10 of the tires, and then on this side I'll have 11 tires left, right? Kind of like a remainder. Chemistry is very similar in the way that we do these chemical equations. We're putting, methane together with something else, or oxygen, and I've got unlimited supply of oxygen, so the only fuel I can make is how much methane I have, right? So stuff like that, you'll see more of these type of problems, and that's why the coefficients are so important. You need to be able to determine the coefficient, balance the equation, and then use that to work these other little problems. Okay? Let me look at this last little practice problem. Um, they do so many, I don't think I'll actually get into that. Yeah, I'm not going to work an example here because I've posted so many of these on the videos, but let me see if there's anything else I need to mention. Like I said, this is a long chapter. Oh, yield. Absolutely, yield. Okay, so the yield is how much we get out. Okay, for example, this was a reaction between ethane and water to create something else. Um, the yield is how much products we get back. And so it'll ask you about theoretical versus actual. The theoretical is if I wrote down I weighed all this out in the beginning, 28.05 grams of methane. And then I did the equation on paper and figured out that I have, so many moles of methane. That's how many moles I should be able to make of this, the C2H6O, but I actually only get a lesser amount. Okay, so that's just the actual versus theoretical. And if you want to figure out a percent, you can just do actual over theoretical times 100. Okay, so let me look at a problem. Was this that problem? Yeah, this is that problem. So in this problem with the ethane right here, we calculated that we would get back 23 grams, but in actuality, we only got back 15 grams ethanol. That's what that is, ethanol. So the yield was 65%. Okay. Now, I don't think we'll do any of that in our lab this week, so I'm not going to stay harping on that. I will do more practice problems on those as we get there and we start doing more chemical reactions. Especially in the lab walkthroughs, we'll go through and kind of do each of these just to make sure that you're getting something close to what I'm getting. Okay? And you always have less actual yield than theoretical yield unless you did something wrong in your calculations or in your experiment. Okay, you're always going to have less than the theoretical because things happen. Some of these molecules won't combine, some of them get lost in evaporation or something like that, and you end up losing that mass that you thought you were going to have. And then we talked about the limiting reactant. They've got bread is left over. I like my little bike equation. So that's how come the coefficients are going to be very important in determining how much yield you can get back. Okay, so limited reactant problems is the hardest that you'll see in this chapter. So if you get to once you get to this portion, I would suggest going and watching these other little videos that I posted in chapter 5. So they do some limiting reactant practice problems. And like I said, that's about the hardest. So if you can get to that point and really understand what's going on there, then you should be perfect with everything else in the chapter. All right. Um, Make sure you got the mole to molar mass down. That's going to be a big portion of your ALEKS objectives, balancing chemical equations, and then getting into these more complex problems where you have to solve the yields and the mass of different equations. Okay, so is that? Let me go to the text real quick and just make sure I didn't miss anything before I let y'all go. I'm coming up on an hour, and I was trying to wrap this up before an hour. They're still talking about formula weight. Yeah, so like I said, the PowerPoints are not very good. If you can load those, if you can download the PowerPoint and then upload it onto Microsoft Office, everything should straighten out, the little blocks there. Otherwise, I would suggest coming to the text because they have it laid out nice and smoothly so you can kind of follow along and work these practice problems. They also got, don't forget about more practice at the bottom, and then obviously ALEKS. Okay, if you go into ALEKS, they have your objectives, but once you get done with your objectives, you can go to the review and then keep working more problems, and it actually will help build your grade too. So if you didn't do quite as well, there is a point where you can start getting those points back even if you missed them earlier on by doing the review questions and just keep working those problems. All right. So if any of this gives you a problem, you can email me. Like I said, I know we covered a lot of material today. Slow down, start over, uh, watch one of the other videos on Cougar View, and then come back to it. And I think everything will start to click and make sense. All right. So that's it for chapter 5, chemical reactions. I will see y'all next time.